Alright, so last time we learned about majorization, right? With majorization, log majorization, and try to figure out what does it mean, right? And today I will just jump ahead. I will not, go on this book, but so I jump ahead to the 6th chapter on eigenvalues, singular values, inequalities, and what there are a lot of inequalities like that, but I would like to share with you about Ando inequality. Quality or norm for unitarily invariant norm. So first, let's talk about norms, right? We know norm, right? We have distance, and then from distance we can define norm. Make sense? I mean, that is for vectors, and for matrices we also have the same thing. If you have some distant functions, you can find the norm of some matrix. So let's consider Mn, where Mn is algebra of all invariant matrices, and a norm is said to be unitarily invariant if norm of A equal to norm of U, A, V for any U and V, for any unitary matrices U and V. So such norm is called unitarily invariant norm. We have a lot of such norms, right? For example, trace norm, we have there is trace of A, absolute A, right? And so for trace, this invariant.
Isn't it true for any number? I wonder if it's true for any number.
No. That's true for any norm. Yeah. You might consider some matrix norm. You see that. So we have students. Do you know what is unitary matrices?
Might put
If you have U star and U equal to U star and equal to identity, and this is conjugate. I mean, you take the transpose of conjugate.
The easy definition is conjugate equals to the inverse.
The inverse, yeah. In this case, the conjugate is equal to the inverse. Unitary matrices are very important in quantum information theory. They play a role like quantum channel, quantum gate. So in classical information, you have the classical gate, logical gate. In quantum information theory, you also have something like that. And unitary matrices play a role like this. Makes sense? Because they preserve norms. All right, so I will not talk too much about that. Let's move to the relationship between unitarily invariant norms inequalities and singular value inequalities. Okay. So if we have some matrix, of course we have eigenvalues of that matrix, right? But that is not singular values. So how to define singular value of matrix A? You consider matrix A star A, right? And this matrix is positive, so you can apply the square root to that matrix. This matrix is called a modulo A. Okay? And then from modulo A, you can consider all eigenvalues of modulo A. And all eigenvalues of modulo A are called singular values of A. This eigenvalue. And this is singular value. Okay, this is how singular values are defined. there's very, very tight relationship between singular values and unitarily invariant norms. It says A less than or equal to B, right? If and only if you have singular values of under A is modelized by singular value of B, or sometimes we just say singular value of A, singular value of B, where all singular values are in the increasing order. So you rearrange vectors of singular values and then you get that. We have that relationship. Okay? So we still have another relationship. And one of very important unitarily invariant norms is key-fan norm. Key-fan norm. Okay? What is that? So for matrix A, the key-fan norm of A we call the K key-fan norm A. Okay. That is sum of singular values of A. The first K, right? For K equal to 1, 2, and so on. So it's K key-fan norm. So if we remember, right? If we remember about majorizations, we will see actually there's some relationship between this sum and majorization. Do you remember that? X is majorized by Y if and only if when you take sum of the first biggest K eigenvalues, right? Of X less than equal to sum of first K eigenvalues of Y. So, and here we have, of course, here we also rearrange, right? We need to rearrange that each time. Each time we need to rearrange that. And the key-fan dominance principle says, key-fan dominance principle says A K less than or equal to BK for any K from 1 to an N. These inequalities imply that norm of A less than or equal to norm of B for any unitarily invariant norm. And for any unitarily invariant. So this is very important, right? So instead of proving norm inequalities, we can just prove such inequalities for key-fan norms. Make sense? So if they ask us to prove some norm inequality, right? So instead of that, we prove for key-fan norm. That's it.
But that's one way only, right? So
yeah, just one way. Yeah, just one way. And in the rest of this lecture, we will study how to prove an Ando inequality using this key-fan norm. The technique is very beautiful, so that's why I choose this inequality to tell you.
But there is no equivalence between a regular norm and key-fan norm, because like, can you go on both sides with certain constants? Because
so you're talking about equivalence, right?
Yeah, but because like two norms are equivalent if one norm, let's say, because it seems like key-fan norm is the strongest one. So, and this.
So if that satisfies, then for other norms also satisfies. That's what you said.
Yeah. I don't know. I'm asking.
I don't know.
Let's implicate. Yeah.
But if we consider key-fan norm, so we have some of that, right?
Yes.
Some of this. So this key-fan norm is nothing but the majorization relationship between A and B. Make sense? So this key-fan, this condition is, implies that actually SA is majorized by SB, right? And so since SA is majorized by SB, so we have no A less than or equal to no.
And this is if and only if.
Yeah. Makes sense? Yeah. All right, so let's move to Ando inequality. Let me formulate that first, and then I try to prove that in 30 minutes. The Ando inequality says F from R plus to R plus is matrix monotone, or let's say operator monotone. Operator monotone. Then norm of f of A minus f of B less than or equal to norm of f of absolute A minus B. So, I mean, sometimes I don't remember, but I talk about operator monotone functions, right? I mean, Dr. Baylor would be very happy to hear about it. Who remember? Do you remember that? Matrix monotone function, operator monotone function. No? Okay, just give you a very brief. You know, we have monotone function, right? I mean, increasing monotone functions, right? Means if you have x less than or equal to y, this implies f of x less than or equal to f of y. Okay? So for matrices, we also have something like that. You have matrix A for Hermitian, let's say Hermitian matrices. If A less than or equal to B, imply f of A less than or equal to f of B. So this case we call matrix monotone function. Okay, matrix, or you know, if that inequality holds for any size of matrices, we call that is operator monotone functions. And operator monotone functions on R plus has very good property because such function can be represented in the form of integrals. And we will use that integration integral.
The function is real valued, right? The function is real valued.
Yeah, the function is real value function. Yeah, the real value function. I repeat that several times, but in case, I mean, this is real value function, and f of A and f of B are defined using
real numbers.
Spectrum theorem.
Yeah, that's understood. Yeah.
Okay. So we talked about that several times, right? Operator monotone functions has following integral representation. F of x equal to A plus bx plus integral from 0 to infinity. Here is we have s plus, or let's say not f of x, that is just have to write it so that we don't have any s of x, s plus x d mu s. Let's say that. So students, I think they did not take the functional analysis, right?
No.
So they don't know about the measure. So just say, but you know integrals, right? You say it's just some kind of measure, right? Just some kind of measure. Or let me write in an incorrect form, but that will not confuse you. Let's say that, okay, I will write something like this. How about that?
Don't try it at home.
Yeah. So let's make that simple, right? Because you know, theory of operator monotone functions is very difficult. It's not easy at all. And basically, we know the existence of that measure, but to construct that measure is almost impossible. Okay, so we'll use this integral representation to prove this. Together, of course, we need to use this given dominance principle. All right? Are you ready with that? So let's go.
So this integral representation, is it for any operator monotone function or?
Yeah, for any operator monotone functions. But for each operator monotone function, there is corresponding measure.
I understand that.
Yeah. So no, the proof is very standard. I just used the idea to get to in my two recent papers, so that's why I tried to show it. So if we analyze, right, the inequality, we have f a, f b, f absolute a minus b. Okay, let's analyze this inequality, and then let's see the function f looks like this. So basically, we don't have need we don't have to do anything with this part, basically. But this is linear. Make sense? So the only thing we need to do is this part. And there's very good thing in this for undergrad function is that undergrad function is this function is operator monotone. The inside function under integral is operator monotone. So the idea is we need to prove this inequality for such function, right? And then we generalize for any operator monotone function. That is the first observation. Make sense? The second observation is following. Here we have absolute A minus B, right? A modulo of A minus B. So of course A and B are comparable. But we might prove the inequality for the case when A greater than or equal to B. Right? When A greater than or equal to B. And then from that case we generalize to for any A and B. Okay? So that is two observations. So based on that we will prove this inequality. Make sense? Okay, now let's see. I will put, so based on that, let's consider two cases. The first case, when A greater than or equal to B, okay? When A greater than or equal to B. So that means we need to prove f of A minus f of B less than or equal to norm of f of A minus B. Okay? And we have to mention that when A greater than or equal to B, f of A is greater than f of B, because f is operator monotone function. So we are good. Most of the things in here are positive, right? So we are good with that. And since A greater than or equal to B, I can put C equal to A minus B. And C is also positive, not negative, let's say that. Positive semi-definite. So instead of this, I can write f of B plus C minus f of B less than or equal to f of C. Right? Less than or equal to f of C. So you see, this is, you have a bigger one, you subtract this, and then you get this, right? And consist for the model. All right, that is the first one. But first, I need to prove this inequality for such function, for this function. I said S x over s plus x, right? Let me denote by f of s x equal to x over sx, x plus x. Let's say that. Okay, this function, if you calculate it, or you see you add x, you add s, and then you subtract x, right? You write x plus s minus s over s plus x. Then you split it down, you get 1 minus s over s plus x. Make sense? And so we simplify, we make our life a little bit easier when we take difference in here. Okay? So again, s is a coefficient, right? Just a number, s1 over s plus 1 is operator monotone decrease. So if we want to prove 1 for such function, we need to prove the following one. So in this case, what is f of 1? F of b plus c, s. Let's say that, right? That is 1 is identity minus s plus b plus c to -1, because the inverse, right? We'll take the inverse in here. Make sense? Take the inverse in here. And then, what's the next? F of sb equal to I minus s plus b to -1, right? See, I just plug b plus c into the instead of x, right? And then, now let's consider the difference. fsb plus c minus fsb. So 1 with 1 will be cancelled out. So since you take this guy, you subtract by this guy, you have s, right? S plus b to -1 minus s. S plus b plus c to -1. Okay? I mean, this is clear. And the thing is, now we if we write this, we say, okay, I can say s plus b to -1, and then something minus s plus b plus c to -1. You know, actually this is very interesting. This is equal to s plus b to -1 times c times s plus b plus c to -1. We have this identity. Looks like that.
It's called Hilbert, no.
I don't know that, but it's,
Hilbert identity.
yeah, it's beautiful. I mean, in order to prove that, we just multiply both sides. For example,